Cool. And I think it's probably time for our poster presentations. Do we have Nadisha or Leon here?
Yes, Leon is here. Yep.
Oh, nice. Do you mind sharing any of your slides if you have any?
Okay. Okay, can you see it? My slides?
Yes.
Okay, so I start then. So my name is Leon Kester, and I'm going to present a paper on epistemic defenses against scientific, wait a minute, right, against scientific and empirical adversarial AI attacks. From now on called CAI attacks. And I read this paper together with Nadisha Marie Aliman. So the motivation for this paper is that we are all confronted already with deep fakes for political disinformation and fake news, but also there's now the possibility of deep fake science. And for CAI attacks, which we use as an umbrella term for malicious AI use, we have to look at deception, sabotage, and disruption in science and engineering. The two cases we discuss in the paper are about cyber threat intelligence and about scientific writing. So already in cybersecurity, experts have already been misled with AI-generated fake cyber threat intelligence text, and cyber defense AI has too. So, and in general, scientists could soon be misled with AI-generated fake research articles, fake data experiments, or fake reviews. There could be some misunderstandings that the CAI attacks would only be about security, not about AI safety. But if science is unable to craft CAI defenses, then it is also a safety problem. So in the paper, we talk about generic features for epistemic defenses against the CAI attacks. One is it should be explanation anchored. 2, that it should be trust disentangled. 3, that it should be adversarial. And these generic features we apply to these use cases of cyber threat intelligence and scientific writing. And this leads us to a complementary 3-layered security framework for each of one. We are under the understanding that epistemic dizziness is inescapable. So for proactive self-paced exposure to synthetic AI-generated material to augment creativity and critical thinking instead of shielding from deepfakes. So, and in the future, that could be research also be possible on language AI that could stimulate human creativity in writing new plausible threat models and defenses in AI and cybersecurity and AI safety. Thank you for your attention.
Thank you, Leon. And do we have our second poster papers author here? Roman, nice.
We do. Let's see if I'm gonna be able to share with you. Can you see my screen?
Yes.
Excellent. So in this paper, I noticed that a lot of people kind of use interchangeably AGI, artificial general intelligence concept, and apply it to human intelligence. So human level intelligence and AGI being kind of synonymous for what people want to say when they want to go beyond narrow AI to systems which can solve problems in multiple domains. But I feel it's a mistake. I think humans are not universally general, and AI has capability, at least, of becoming universally general. So I start the paper by motivating some examples for limitations of what humans cannot do, even trivial things like basic algebra or trivial memorization, like phone numbers and names. And it becomes quite obvious that if you took truly human intelligence and automated it and said, okay, I created AGI and Google or Facebook released it, people would laugh at you pretty hard because your system would not be able to do those basic things. Others seem to be also noticing that when we talk about human general intelligence, we mean in a domain of human expertise. We are very good at doing human things, social navigation, geographic navigation, things humans have evolved to be good at. But there seems to be almost an infinite universe of problems which are not in a human domain. Some are in the domain of animal intelligence, others are mathematical problems, which we have very little capability of solving, and not even awareness that they exist, that those problems out there, and that we have absolutely no competitive capabilities. This is, of course, why I'm interested in it from safety point of view. AI doesn't have to be better than us at everything to be dangerous. It's sufficient that it's dominating a few strategic domains, important domains where humans cannot perform as well, or we're not aware that domain even presents a problem. So in a paper, I try to both motivate weakness of HLI model and give some examples of what it is AGIs can do, which if a human was able to do would seem almost magical, like estimating face from voice or from DNA or from ear shape, or looking at scans, medical scans of different parts of a body to predict gender, age, smoking status, of things of that nature. And as we develop AI more and more, there is more and more examples of such situations. So all of it falls into this directions of research. I presented yesterday about uncontrollability of AI. There are also limits to explainability, what we can comprehend and what we can predict about AI. It now appears that there are also whole domains of knowledge in which we would not be able to fully participate and would have to trust AIs to tell us what's going on there. So if you're interested in this, stop by my poster, I'll tell you more. Thank you.
Thank you for sharing, Roman. Do we have Christopher here?
Yes, here I am.
Great.
So I'm just going ahead and sharing my slides. And here it is. So can you see my slides and can you hear me?
Yes, perfectly.
Okay, great. Let me just minimize that. Yeah, there it is. So hi, everyone. I'm Chris Lazarus. I'm going to briefly talk about a recent contribution that we had in the field of neural network verification, where we basically demonstrated the use of mixed integer programming, specifically with binarized neural networks for the purposes of neural network verification. So, yeah, there it is. So very quickly, I guess a brief motivation for this is, as we know, neural networks are being used, are being widely adopted for more and more applications. And one of the, even though they're very powerful and they often serve as universal function approximators, a big issue that we have is that we think of them as black boxes. And what that means is that as humans or engineers, we don't have a very clear notion of what their transfer function looks like. And overall, it's really hard to reason about them and to be able to trust them. And if we ever intend to use them in cyber physical applications or any other application that has kind of like a safety or critical mission aspect to it, most likely if it's physical systems interacting with humans or any other kind of like decision-making process that involves ultimately humans, we want to be able to assess their safety and trust them. And so the fundamental situation or problem here is that often when we test models that incorporate neural networks, we do so in a statistical manner. And that what that means is we sample points in the input and we see what the output looks like. This is pretty much kind of like, I guess like the key idea behind, you know, like robustness analysis or adversarial defenses and so on. But what this image is trying to depict is that even though if we do sample-based testing, and sure, here we can see that most of the points that we sampled in the input space, which would be the horizontal axis, fall within our desirable output region, which is a green square. Still, there are still spikes that fall beyond that, and we just failed to sample that. And it is also well known by now that neural networks are kind of like prone to extreme discontinuities and so on. And so I think this is the high level image of verification, which is sure, if we look at something like a policy that controls, let's say, an aircraft in this case, or a collision avoidance system, for those that are more familiar with that benchmark, and we sample a bunch of points and we really zoom in, we can see that the space is just filled with a finite collection of discrete points, but verification goes beyond just taking just a bunch of points and actually kind of like formally filling out that space between them and concluding formally that there's no such counterexample. In kind of like concrete mathematical terms, what that means is that we define an input set, big X, and an output set, big Y, and what we want to confirm is whether all the points in the input set map to the points in the output set. Turns out this approach is basically, well, compared to testing, it's sound, but it's very computationally costly, so it's not really scalable. And a lot of work has been done around this, and there are many different approaches. There are many different types of algorithms, but more concretely, in this specific work, we have tried to do is, there has been recent work in model compression and specifically network quantization. The most extreme case is using binary neural networks, which basically use one single bit per parameter. And when that is the case, and of course, there's no time to go into the technical details, and I don't expect this slide to help elucidate in any way how it works. But basically, when we use binary neural networks, we're often able to solve similar problems to full precision neural networks, similar problems with like very little performance degradation. And we can take advantage of other kind of like mathematical machinery to solve this problem. And we're able to, without sacrificing a lot of performance, verify similar properties at a way faster speeds. And that could maybe lead to allowing the use of bigger and bigger models. I think we've run out of time, but I just think the key takeaway and one idea that guides our research is that formal verification is very important for safety critical systems. Thank you.
Thank you so much, Chris. And that is the end of our session for the third session of the AI safety workshop. So I want to thank again for our keynote speaker, Professor Simon Burton, and all of our authors that just did their presentation, and also the panel discussants, Mauricio and Jose. And so for we will have a 20-minute break next, and we will come back at 2:30 p.m. So during which time you are feel free